Hello everyone, this is audio recording for visually impaired students. Let's start chapter phenol from modern organic chemistry. Phenols. Introduction. Phenols are aromatic hydroxy compounds in which the hydroxyl group is directly attached to an aromatic ring. They may be represented by the general formula AROH, where AR represents a phenyl, a substituted phenyl, or some other aryl group such as naphthyl, depending upon the number of hydroxyl groups attached to the aromatic ring. The phenols may be classified as mono, di, trihydric phenols, and so on. For example, we have phenol, orthocresol, resorcinol, pyrogalol. The hydroxyl group attached to the aromatic ring is known as phenolic group. As already stated in chapter 3, phenols are different from aromatic hydroxy compounds in which the hydroxyl group is present in the side chain. The latter type of compounds are in fact aryl substituted aliphatic alcohols, and their behavior is similar to that of aliphatic alcohols. However, both phenols and aromatic alcohols resemble each other in undergoing the electrophilic aromatic substitution and in certain other respects. 2.2 Nomenclature of phenols. The simplest member of phenols is always known by its popular name phenol, although its IUPAC name is benzenol. All substituted monohydric phenols are named as derivative of the simplest member of the series, that is phenol. However, methyl phenols possess special common names. The positions of substituents with respect to OH group are denoted by OM and P in the common system, but by numbers in the IUPAC system, with the OH group carrying the number 1. The following examples illustrate the methods of naming phenols. The names given in brackets are common names: phenols, 2-chlorophenols, 2,4-dinitrophenol, 2-methylphenol, 3-methylphenol, 4-methylphenol. The di and trihydric phenols have the IUPAC name benzene-diols, benzene-triols respectively, but most of them are known by their special names as given below: 1,2-benzene-diol, 1,3-benzene-diol, 1,4-benzene-diol, 1,2,3-benzene-triol, 1,3,5-benzene-triol, or 1,3,5-trihydroxybenzene. It should be noted, however, that when a compound contains some functional group such carboxylic acid esters or carbonyl group in addition to phenolic group, the compound is named hydroxy derivative of the acid, ester, or carbonyl compound. For example, 4-hydroxybenzaldehyde to 4-hydroxybenzoic acid, ethyl 4-hydroxybenzoate. 2.3 Structure and bonding. Phenols are compounds having a hydroxyl group directly bonded to benzene ring, while oxygen of hydroxyl group is in sp3 hybridized state. The carbon of the benzene ring to which oxygen is bonded is in sp2 hybridized state. Resonance interaction takes place between a lone pair of electrons on oxygen and the benzene ring, so that phenols exist as resonance hybrids of resonating structure as shown below. Due to resonance, the carbon-oxygen bond acquires some double bond character and becomes shorter and stronger than the carbon-oxygen bond in alcohols. At the same time, oxygen acquires a slight positive charge, due to which it attracts the electron part of OH bond strongly towards itself. As a result, the OH bond in phenols becomes more polar than in alcohols. Due to above structural features, phenols are differently from alcohols in many respects and are treated as a separate class of compounds. Methods of formation. The commonly employed general methods of preparation of phenols are described below. Number 1. Hydrolysis of diazonium salt. This is probably the most convenient method of preparation of phenols. The reaction is usually carried out by slowly adding diazonium salt solution to excess in boiling dilute sulfuric acid. Since hydrolysis is carried out under very mild conditions, other groups in the molecules of diazonium salt are not affected. Number 2. Alkali fusion of sulfonates. In this method, phenols are obtained by fusion of sodium salts of aromatic sulfonic acids with sodium hydroxide, following by acidification. ArSO3Na plus 2NaOH in presence of Na2SO3 minus an elimination of H2O gives ARONA. On adding HCl gives AROH plus NaCl. This method cannot be applied to salts of sulfonic acids containing substituents such as ClNO2COOH due to possibility of various side reactions. Number 3. From isopropyl benzene cumene. This method is used particularly for the large-scale preparation of phenol from isopropyl benzene, popularly known as cumene. Cumene is readily oxidized by air to form cumene hydroperoxide, which is converted into phenol and acetone by treatment with an aqueous acid. Mechanism. The mechanism of conversion of cumene hydroperoxide into phenol involves series of 5 steps as shown below. In step 1, peroxide gets converted into a protonated peroxide from which a water molecule is eliminated to form an intermediate having electron-deficient oxygen. In step 3, a 1,2 shift of the phenyl group takes place, giving a carbocation which is a resonance hybrid of two structures. The carbocation takes up a molecule of water. Step 4, to form a hemiacetal. The hemiacetal finally breaks in step 5 to yield phenol and acetone. It may be noted that cumene itself is obtained by a Friedel-Crofts reaction between benzene and propylene in the presence of ferric chloride. Number 4. From aryl halides, substituted phenols having electron withdrawing groups like NO2 group in ortho-para positions to the OH group can be easily prepared from the corresponding aryl halides by treatment with aqueous sodium hydroxide. Phenol itself is also manufactured by this method of heating chlorobenzene with 10% sodium hydroxide solution at 603 to 623 Kelvin under a pressure of 200 atm in the presence of copper salt. The process is known as Stowe process. Number 5. From phenolic acid, distillation of sodium salts of phenolic with soda, slime yields phenol. For example, sodium salicylate plus NaOH in presence of CO gives phenol and plus Na2CO3. Number 6. From Grignard reagent, phenols may be prepared by treating an aryl magnesium bromide with oxygen followed by hydrolysis of the product. 2AR-MgBr on adding O2 gives 2ARO-MgBr on adding H2O positives gives 2AROH plus 2MgOHBr. From coal tar, phenols and creosotes are also obtained on a large scale from the middle oil fraction obtained on the distillation of coal tar. Physical properties. Number 1. Physical state. Pure phenols are generally colorless liquids or solids, but they usually appear slightly colored as they readily get oxidized even in air, and the oxidation products are color compounds. At the same time, substituents like NO2 also impart color to phenols. Number 2. Boiling points. Due to the formation of intermolecular hydrogen bonding, phenols but considerably higher than corresponding hydrocarbons and aryl halides which do not contain hydrogen bonds. For example, phenol boils at 455 Kelvin while toluene boils at 384 Kelvin only. Number 3. Solubility. Phenols are practically insoluble in water, although phenol itself and some di- and trihydric phenols are fairly soluble. The solubility of these compounds is probably due to the formation of hydrogen bonds with water, but the extent of hydrogen bond formation is very small due to the large size of phenyl group, which marks the polar character of OH group. All phenols are soluble in aqueous alkaline solution due to the formation of water-soluble salts. Phenols containing substituents such as NO2 can also form intramolecular hydrogen bonds. This is responsible for certain interesting observations. For example, orthonitrophenol has a lower boiling point and smaller solubility in water than its meta or para isomer. This is because the orthoisomers form intramolecular hydrogen bonds between the oxygen of nitro group and the hydrogen of hydroxyl group. This phenomena is also known as chelation. Due to the intermolecular hydrogen bonding or chelation, the orthoisomer has only very small tendency to form intermolecular hydrogen bonds. On the other hand, in the meta and para isomers, the hydroxyl and nitro groups are situated that intramolecular hydrogen bonding is not possible while intermolecular hydrogen bonding takes place. As a result, meta and para nitrophenols have higher boiling points and are also soluble in water. Chemical properties. Phenols are highly reactive compounds which combine the reaction of both the hydroxyl group and aromatic ring. The important reactions of phenols are discussed below. Reactions of phenolic group. Number 1. Acidity. Phenols are weakly acidic compounds. They react with aqueous alkali metals hydroxides to form salts known as phenoxides. AROH plus NaOH gives ARONA plus H2O. However, phenols do not react with aqueous carbonate or bicarbonates. However, the salts of phenols are converted into phenols by aqueous mineral acids, carboxylic acids, or even carbonic acids. This observation indicates that phenols are very weak acids, weaker than carboxylic acids or even carbonic acid. This is confirmed by comparison of their acidity constant values or pKa values, while phenols have Ka value of the order 1 into 10H to power minus 10. Carboxylic acids and carbonic acids have K values of 1 into 10 to power minus 5 and 1 into 10 to power minus 7 respectively. These days, acidic strength are usually represented in terms of pKa values, which is the negative logarithm of acidity constant, that is pKa is equals to minus log Ka. It may be noticed that a stronger acid has larger Ka value but smaller pKa value, while a weaker acid has smaller Ka value but larger pKa value. Even though very weakly acidic themselves, phenols are much more acidic than alcohols, which have Ka value of the order 1 into 10 to power minus 16 to 10 to power minus 18. This appears to be rather surprising since both phenols and alcohols are characterized by the presence of hydroxyl groups. What then is the reason that an OH attached to an aromatic ring is so much more acidic than an OH attached to an alkyl group? We would attempt to answer this question by considering the stability of the ions formed relative to the stability of unionized compounds. Explanation of acidic character. The ionization of phenols is an equilibrium reaction involving the unionized phenol and phenoxide and hydronium ions. For example, C6H5OH plus H2O in equilibrium with C6H5O plus H3O positive. Now, neither phenol nor phenoxide ion can be represented by only one valence bond formula. On the other hand, each of them is a resonance hybrid of various contributing structure as shown below. It may be noted that the contributed structure C, D, and E of phenol involve separation of charge and are therefore less stable than structure A and B. On the other hand, in case of phenoxide ion, none of the contributing structures involves charge separation and the structures are almost equally stable. As such, phenoxide ion is resonance stabilized to a greater extent than phenol. Therefore, the equilibrium between phenol and phenoxide ion favors the formation of phenoxide ion and hydronium ion. That is, phenol plus H2O gives phenoxide ion plus H3O positive. This accounts for the acidic character of phenols. Comparison with alcohols. In case of alcohols, the equilibrium reaction involving alcohol and alkoxide ions does not favor the formation of alkoxide ion and hydronium ion. This is because there is no resonance stabilization of alkoxide ion relative to alcohol, since neither the alcohol nor the alkoxide ion exhibits resonance. Hence, it should not be surprising that compared to alcohols, phenols ionize more readily to form phenoxide ion and hydronium ion. In other words, phenols are more acidic than alcohols. Effect of substituents on the acidity of phenols. The acidity of phenols is strongly influenced by their substituents attached to the benzene ring and their position. This is because the state of equilibrium in the reaction between phenol and water to furnish phenoxide ion and the hydronium ion depends upon the stability of the products relative to the stability of the reactants. An effect which stabilizes the phenoxide ion more than the parent phenol should increase the acidity, while any other factor stabilizes the phenoxide ion should decrease the acidity, as illustrated below. Number 1. Nature of substituents on benzene ring. A. Electron withdrawing substituents. Phenols having electron withdrawing substituents such as the halogens and nitro groups are more acidic than phenol itself. This is because an electron withdrawing group attracts the electron towards itself and thus disperses the negative charge of the phenoxide ion. As a result, it stabilizes the phenoxide ion and increases the acidity of phenol. B. Electron releasing substituents. Phenols containing electron releasing subgroups such as alkyl groups are less acidic than phenol itself. This is because an electron releasing substituents release the electron away from itself and thus intensifies the negative charge on the phenoxide ion. In this way, it destabilizes the anion and thereby decreases the acidity of the phenol. In short, electron withdrawing groups increase the acidity of phenol while other electron releasing groups decrease their acidity. Number 2. Position of substituents relative to hydroxyl groups. Apart from the nature of the substituent, the position of the substituent relative to the hydroxyl group also has large influence on the acidity of phenol. This may be explained as follows. Number 1. The stabilizing or destabilizing influence of the substituent operates through inductive effect as well as resonance effect. Number 2. The intensity of inductive effect of the substituent decreases as its distance from the OH group increases, that is ortho position greater than meta position greater than para position. That is why acidity of chlorophenols is in the order. Number 3. The resonance effect is more pronounced if the substituent is in ortho or para position than in meta position. To understand this, let us examine the contributing structures of ortho, meta and para nitrophenoxide ions. It may be seen that each of ortho and para nitrophenoxide ions is a resonance hybrid of 5 contributing structures in one of the structures. In each case, conjugation is extended up to oxygen atom of the nitro group, but no such conjugation is possible for meta nitrophenoxide ion and has only 4 contributing structures. The net result is that there is a greater resonance stabilization of ortho and para anions than the meta isomer. As such, ortho and para nitrophenols are much stronger acids than meta nitrophenol. An interesting observation is that certain phenols having electron withdrawing groups in the ortho position are weaker than para isomer. For example, orthofluorophenol is a weaker acid than parafluorophenol and orthonitrophenol is a weaker acid than paranitrophenol. This can be attributed to the formation of intramolecular hydrogen bonding in case of orthoisomer as shown below. Number 2. Ether formation. Williamson synthesis. On reaction with alkyl halides or dialkyl sulfonates in alkaline medium, phenols are converted into corresponding alkyl esters. The alkyl halides or sulfates undergoes nucleophilic substitution by the phenoxide ion present in alkaline solution of phenols. Thus, we have AROH plus NaOH gives ARO negative Na positive plus H2O. Claisen rearrangement. This is an interesting rearrangement of reactions involving aryl-allyl ethers. When heated to 475 Kelvin, the allyl group of the ether migrate from ether oxygen to the ring carbon at ortho position. For example, allyl phenyl ether at 475 Kelvin gives ortho-allyl phenol. If both the ortho positions are already occupied, the allyl group migrates to para position. For example, allyl 2,6-dimethyl phenyl ether at 475 Kelvin gives 4-allyl 2,6-dimethyl phenol. Mechanism of ortho rearrangement. Orthoisomerism involves a concerted mechanism in which the cleavage of allyl oxygen bond is synchronized with the formation of allyl carbon bond at the ortho position. The cyclohexadienone intermediate thus formed undergoes a tautomeric change to give ortho-allyl phenol in which the ring regains the aromatic character as depicted below. It may be carefully noted that it is the gamma carbon of the allyl group which attach itself to the ring carbon. This is supported by the fact that ortho migration involves as an inversion in the position of substituents in the allyl group with respect to that of starting compound. For example, mechanism of para rearrangement. Para isomerism involves 2 stages. In the first stage, orthomigration takes place and cyclohexadienone intermediate is formed, but this intermediate cannot undergo tautomerization since there is no hydrogen at ortho position. As such, the intermediate undergoes another migration of allyl groups, ultimately yield the final product. It may be noted that in para-isomerization, 2 migrations takes place, each of which accompanied by inversion. In other words, one inversion is followed by another inversion. So there is no net inversion in the position of the substituents with respect to the starting compound. For example, number 3, ester formation acylation. Like alcohols, phenols are converted into esters by reaction with carboxylic acids, acid chlorides or anhydrides. However, in actual practice, esterification is better carried out by the use of acid chlorides or anhydrides in the presence of either an acid or base such as pyridine. Benzolization of phenols is usually carried out in presence of aqueous NaOH since benzoyl chloride is not easily hydrolyzed by alkaline. The reaction is called Schotten-Bowman reaction. For example, mechanism: to start with, the alkali attacks the phenols to form phenoxide anion. This anion undergoes nucleophilic attack on the carbonyl carbon of the acid chloride to form a tetrahedral intermediate. The intermediate then loses a chloride ion to form the ester. Fries rearrangement: if an ester of a phenol is heated with aluminium chloride, the acyl group migrates from the phenolic oxygen to the ortho or para position on the ring. This is called Fries rearrangement. At low temperature, para product predominates, while at high temperature, orthoisomer is the main product. Mechanism: the rearrangement probably involves the formation of an acylium ion, which then attacks the aromatic ring, as in Friedel-Crafts acylations. The complete mechanism may summed up as follows. Number 4. Reaction with zinc dust. When distilled with zinc dust, phenols form corresponding hydrocarbons. For example, phenol plus zinc on heating gives benzene plus ZNO. 5. Reaction with ammonia. When heated with ammonia at high temperature pressure in the presence of catalysts like anhydrous zinc chloride, OH group of phenols is replaced by NH2 group. Reactions of aromatic ring. Electrophilic substitution. Phenols readily undergo electrophilic aromatic substitution reactions. The OH group linked to an aromatic ring activates the ring to the electrophilic substitution and directs the incoming group to ortho and para position. In fact, the OH group is a very powerful activator, and unless precautions are taken, polysubstitution takes place. Explaining of ortho-para directing and activating influence of OH group towards electrophilic substitution. The ortho-para directing and activating influence of OH group towards electrophilic aromatic substitution can be explained in terms of the assumption that oxygen of this group can share more than one pair of electrons with the ring due to resonance. When phenols undergoes electrophilic substitution, the contributing structures of the intermediate carbocation formed by the attack of the electrophile at ortho, para, and meta positions are shown below. The carbocations formed by ortho attack is resonance hybrid of four structures 3A and 3D. Of these four structures, the structure 3D is particularly stable since in each atom, except hydrogen of course, has a complete octet of electrons. Similarly, in para attack, the carbocation is a resonance hybrid of four structures 4A and 4D, of which 4D is the most stable. But in case of meta attack, the carbocation is a hybrid of only three structures 5A to 5C, there being no structure corresponding to 3D and 4D. This means that positive charge of the ortho and para ions is dispersed over more atoms than is that of metal ion. It is therefore apparent that the hybrid carbocation resulting from ortho and para attacks are more stable than the carbocation resulting from the meta attack or from the attack on benzene itself. Thus, substitution in phenols occur mostly at ortho and para position and occurs at faster rate than in case of benzene. The important electrophilic substitution reaction of phenols are described below. 6. Halogenation. On treatment with halogenation, phenols are very rapidly halogenated, forming polyhalogen derivatives. For example, reaction of phenols with an aqueous solution of bromine immediately produce a precipitation of tribromophenol. In fact, the reactivity of phenols towards halogenation is so great that even substituents like SO3H group, if present in ortho or para position, get displaced. Halogenation can, however, be limited to monohalogenation stage by performing it at low temperature and in non-polar solvents such as carbon tetrachloride or carbon disulfide. The above observations can be explained in terms of the fact that greater the electron density around benzene ring, the more easily it can undergo electrophilic substitution reactions. In aqueous solution, the phenol ionizes to form phenoxide ion. Due to the presence of negative charge on it, oxygen of the phenoxide ion releases electrons towards the benzene ring to a large extent. As a result, electron density around benzene ring becomes very large, so that the ring is highly activated and undergoes tri-substitution. In polar solvents such as CH2, phenol does not undergo ionization to an appreciable extent and occurs mainly as unionized molecules. The OH group of phenol can release electrons towards benzene ring only to a small extent. As a result, benzene ring is not strongly activated and therefore it undergoes only monosubstitution reaction. Number 7. Nitration. Nitration of phenols gives poor yields of the expected nitro compounds. This is because phenols are easily oxidized and nitric acid can bring about not only nitration but also oxidation of the starting phenol. Use of concentrated nitric acid in the above reaction leads to the formation of 2,4,6-trinitrophenol or picric acid in the low yields. Sulfonation. Sulfonation of phenols proceeds readily to the yield either the ortho or the para isomer as the main product depending upon the temperature of the reaction. In general, low temperature favors the formation of ortho isomer while high temperature favors the para isomer. On heating to 373 Kelvin, orthophenol sulfonic acid changes to the thermodynamically most stable paraphenol sulfonic acid. 9. Friedel-Crafts alkylation. Phenols undergo Friedel-Crafts alkylation forming predominantly para-isomers. The reaction is carried out in the presence of HF. Normally, Friedel-Crafts reaction is carried out in the presence of anhydrous AlCl3, but in case of phenol, this catalyst is not used. This is because electron deficient Al atom of AlCl3 coordinates with a lone pair of electrons on oxygen of OH group to form a complex. This suppresses the activating influence of OH group so that the yield of the product is very poor. 10. Friedel-Crafts acylation. Phenols can also undergo Friedel-Crafts acylation to form ortho and para-hydroxy ketones by treatment with acid chlorides and acid anhydrides, but the hydroxy ketones are generally prepared by Fries rearrangement. 11. Pt.N.R.S synthesis. When treated with a mixture of hydrogen cyanide and hydrogen chloride in the presence of anhydrous aluminum chloride, phenols give phenolic aldehydes. The reaction known as Pt.N.R.S synthesis constitutes an important method for synthesizing phenolic aldehydes. The aldehyde group gets attached preferably at para position. Mechanism. Pt.N.R.S synthesis is an electrophilic aromatic substitution in which the attacking reagent is formaldinium ion formed from HCN and HCl in the presence of anhydrous AlCl3. The complete mechanism may be summed up as follows. Number 2. Hoban-Hosch reactions. This is an acylation reaction of polyhydric phenols having hydroxyl groups in meta position with each other. It is carried out by treating such phenols with alkyl cyanide and hydrogen chloride in presence of anhydrous zinc chloride or aluminium chloride followed by hydrolysis. For example, mechanism of the reaction is similar to that of Gattermann reaction and is summed up below. Special reactions of phenol. Coupling with diazonium salts. When treatment with diazonium salts in weakly alkaline solution, phenols undergo coupling to form hydroxo compounds. For example, benzene diazonium chloride plus phenols on weakly alkaline medium gives para-hydroxy azobenzene plus HCl. 14. Kolbe reaction, also called Kolbe-Schmidt reaction. Carboxylation. When heated with carbon dioxide under pressure, sodium salts of phenols undergo carboxylations to form salts of phenolic acids, the orthoisomers being the main product. For example, when sodium phenoxide is heated with carbon dioxide under pressure, sodium salicylate is obtained as the major product. Mechanism. The mechanism of Kolbe reaction is believed to involve the electrophilic attack carbon dioxide on the phenoxide ion as shown below. Number 15. Reimer-Tiemann reactions. On heating with chloroform and an alkali, phenols are converted into phenolic aldehydes and an aldehyde group being introduced onto the aromatic ring, generally in ortho position to the OH group. For example, when phenol is heated with chloroform and aqueous sodium hydroxide, salicylic aldehyde is obtained as the main product along with a small amount of the para-isomer. Mechanism. The mechanism of the reactions involves the electrophilic substitution of phenoxide ion formed in solution by the action of alkali on phenol. The attacking electrophilic reagent is the electron deficient dichloromethylene CCl2, a carbene generated by the action of alkali on chloroform. Dichloromethylene is electrically neutral, but it acts as an electrophilic reagent as the carbon atom present in it is surrounded by only 6 valence electrons. The complete mechanism may be summed up as follows. If carbon tetrachloride is used in place of chloroform in Reimer-Tiemann reaction, phenol give rise to phenolic acids. For example, 16. Ledger-Mannes reactions. Phenols undergo condensation with aldehydes in the presence of an acid or base as a catalyst. The product initially formed get polymerized to form commercially important monomers. For instance, when phenol is treated with formaldehyde in the presence of an acid or alkali, a mixture of ortho and para-hydroxybenzene alcohol is first formed. Alcohols formed undergo polymerization to form a resinous polymers called bakelite. Mechanism of initial condensation. The initial reaction between phenol and formaldehyde involves the electrophilic attack of formaldehyde on phenoxide ion or protonated formaldehyde on phenol as summed up below. 17. Phthalate reactions. On heating with phthalic anhydride in the presence of concentrated sulfuric acid or anhydrous zinc chloride, phenols are converted into phthalates. For example, phenols form phenolphthalein as shown below. Phenolphthalein is used as an indicator in acid-alkali titration. It is colorless in acidic medium but changes to pink color in alkaline medium. 18. Reaction with ferric chloride. Phenol gives a violet coloration with ferric chloride due to the formation of water-soluble complex ferric phenoxide. Other phenols also form colored complexes on treatment with ferric chloride. The reaction is used as an important test in the identification of phenol. This test is not given by alcohols. 19. Lieberman's reaction. On treatment with sodium nitrite dissolved in concentrated sulfuric acid, phenols gives a red color. The color changes to blue on addition of aqueous sodium hydroxide. The reaction is known as Lieberman's reaction. Thank you.